Hello, am I audible?
Yes, you're fine.
Yes, I see your slides.
Hello,
Hello, Mohan. We can see your slides.
hello.
Yeah. We can see and hear you, but maybe you cannot hear us.
Yeah, we should give some.
Am I audible?
We can hear you. Can you hear us? That is 1, 2, 3. We can Lehmer-type conjectures and open problems for Nathanson's totient functions. Can you hear us, Mohan?
Hello. Am I audible now?
Yes, yes.
Sorry, yeah,
Uh,
am I audible now?
yes. Yeah.
Yeah, now I can hear you. Yeah, okay.
Okay.
So my screen is visible. My slides are visible.
Yes. Yeah.
Okay. So yeah, I can start. Yeah. So thank you. First of all, I would like to thanks to organizers, especially Nathanson sir, for giving me this opportunity. Uh, so I'll talk on Nathanson's torsion function for the next few minutes. Mainly, I will discuss some analogous problems, conjectures, analogous to lemma, and some other open problems that arises while studying these conjectures associated with Nathanson torsion functions. So, these are my outline of my talk. Initially, I'll define the Nathanson torsion function and then discuss lemma conjecture and some divisibility phenomena. And at the end, I will discuss some open problems. So the Euler torsion function is defined as the number of positive integers lie between 1 to n, which is co-prime to n. So this is like a GCD, greatest common divisor of n and k. We count such k. Nathanson generalized this in 2007. Instead of just taking single k, can we replace this by a set? So they define torsion functions in this way. Let A be a non-empty subset of 1 to n, the interval 1 to n. And then phi n, Nathanson torsion function, which is denoted by this phi n, And this counts actually the number of subsets A for which the GCD, greatest common divisor of GCD of A and N is 1. Where the GCD of A means the number of elements, the GCD of elements of the set A. And if we restrict the set A of size K, then this is denoted by phi Kn. And interestingly, we can observe that if k is equals to 1, this Nathanson torsion function is actually overlapped with Euler phi function. One can see this list on integers and encyclopedia, where the phi and the sequence is listed over there. Yeah. So the very first result was given by Nathanson in 2007, where they explicitly give the formulas for both the functions for phi n and phi k. Surprisingly, we can observe that this phi n contains mostly subsets, so we are not worried about the size. So that's why I think this power 2 we can see, and when the size is explicitly k, that's why we have this n over d choose k, and where mu is the Mobius function. Later, several other people also studied these two functions, but for different sets. Uh, it was generalized for the set start with m plus 1 up to n, and later it is again generalized for some arbitrary arithmetic progression. Some other properties of these functions has been studied, like the recursive nature or the periodic nature. But personally, I got motivated. Why I started studied these two function is this particular result, that phi n never be a perfect square except one. So, we asked a very simple question that can we study the similar type of problems that we already studied in case of Euler-type function. So we have this Lemma conjecture which is still open. This says that if phi n divides n minus 1, then n must be a prime. So our main objective is to formulate and analyze such analog for Nathanson torsion functions. So here we can see this phi n divides 2 raised to power n minus 2. Why this 2 raised to power n minus 2? Because the maximum value of phi n is 2 raised to power n minus 2, and which is similar to the Euler-phi function. The maximum value of phi n is n minus 1. In fact, that attains for primes. The same case is true in this case also. In case of Nathanson torsion function, this phi p is actually equals to 2 raised to power p minus 2. So the natural question is, does this phi n divides this implies n is prime or not? Similarly, this phi k n divides n choose k implies n is prime or not. And in this direction, we actually proved these. We have proved these results. So phi n divides 2 raised to power n minus 2 if and only if n is prime. And in case of phi kn, we establish if phi 2n divides nc2 if and only if n is prime. And if phi 3n divides nc3, n is an odd prime except n is equals to 4. In case of 4, we also got some other composite numbers for which this divisibility holds other than other composite numbers. And one can see there is this pattern actually continue. So we can also say that for large k, there always exists some finite number of composite integers, positive integers, except those finite. If this phi kn divides nck, then n must be a odd prime. So the proof of second one is a little bit long, but the proof of the first theorem is quite short, so that we can see. So here we have the very first equation, which is with formula, which was given by Nathanson, and we just simply simplify this formula and this Mobius function. So we got the second one, and for composite n, we can easily establish this inequality. And one can easily observe that for composite n, the phi n is always less than equals to 2 raised to power n minus 4. And if we assume that phi n divides 2 raised to power n minus 2, then this last inequality also holds. So simply substitute these two, second and third, in the last inequality. One can easily obtain the contradiction. So that actually proves n must be a prime. And we even using those two equations, or in even the inequality, we obtained a very nice lower bound for phi n. Phi n is at least 2 raised to power n minus 1, and this bound is very interesting, and not only interesting, this actually gives another property of this function. Phi n is a strictly increasing function, and one can easily prove this one-line proof. Phi n is less than equals to 2 raised to power n minus 2, less than 2 raised to power n minus 1 minus 2, and which is, of course, less than phi n. So this proves that phi n is strictly increasing, but the same thing is not true in case of phi kn. Phi 2n, in particular, phi 2n is not strictly increasing. One can easily see that phi 2 16p is same as phi 2 15p. For any prime p greater than equals to 7. And these are this is like very elementary property, but why we have studied these properties is in this. We answer this question in this slide. So we have this classical conjecture Lemma, and analogously we have established for phi n Nathanson torsion function, which is true. But the Carmichael conjecture for Euler-phi function, which is for every m, there exists at least one m which is not equal to n, with the phi n is equals to phi m. But this is false actually in this case of Nathanson torsion function. And similarly, the Ardosh problem, which is there are infinitely many n for which phi n is equals to phi n plus 1, which is again false in this case because of the strictly increasing nature of Euler Nathanson torsion function. Similarly, we have this comparison of phi kn and Euler-phi function. Again, the Lemma conjecture, we have already established this. For k is equals to 1, it is easy to observe that we can always find some composite number. for which this hold, but n is not prime. For k is equals to 2, we have already proved, and for k is greater than equals to 3, it is false, because we can always obtain some composite number for which this divisibility holds. Again, the Carmichael conjecture, which is for k is equals to 1, this phi k, phi 1 n is again not the Euler phi function. So this is again open. But for k greater than equals to 2, it is false. And similarly, we can see the Erdos problem. And this is again open in this case. So in the previous slides, we have we saw some results which is related with when phi n divides another number. Now the next few slides we will see when a number divides phi n or not. And this actually motivated by this classical fact that if d divides n, then phi d always divides phi n. Like phi d divides phi n. So the same we can ask for this Nathanson torsion function, but unfortunately we got a negative answer here. If omega d means the number of distinct prime divisor is at least 2 in the prime divisor of d, then we can see this phi 2p divides phi 2p square, but phi 2p does not divide phi 10 for any prime p greater than equals to 7. But we have some partial analog. If we restrict this omega d is equals to 1, then we have a very nice result that phi d always divides phi a. And this result we have used to prove this corollary, which was established by Ayad and Kale in 2009, that 6 always divides phi n for all n greater than equals to 3. And the proof is very simple. One can see this phi 4 divides phi 2 raised to power k, because 4 can be written as a 2 square. So from this particular result, the partial analog of this result, we can easily see that phi 4 always divides phi 2 raised to power k for any k, and 6 always divides phi 4, because phi 4 is 12. So 6 divides 12. So directly we can conclude if any n is of the form power of 2, then 6 always divides phi 2 raised to power k. And if there exists any prime p which is greater than equals to 3, odd prime, which divides n, then phi p is always divisible by 6, because phi p is 2 raised to power p minus 3. So 6 always divides 2 raised to power p minus 2. And that from the previous result, we can say that phi p divides phi n. So 6 divides phi n for all n greater than equals to 3. But the surprising result is that 6 is the largest such integer for which this holds. That means 6 is the largest positive integer, such that 6 divides phi n. In fact, we can easily prove that there are infinitely many, for every m, there are infinitely many n, such that m does not divide phi n. In another way, we also obtain this result that if m is a positive integer, then there exists infinitely many positive integer n, such that m divides phi n. In particular, m divides phi n. This is surprising. This m always divides phi n. And the proof of this theorem rely on this lemma, that p raised to power alpha divides phi of p raised to power alpha, and using a simple argument of Chinese remainder theorem, we can easily establish this result. So here we have, since the 6 divides phi n for all n greater than equals to 3, so it is natural to ask, because phi n is a multiple of 6, so we can ask whether there contains infinitely many, where there are infinitely many primes of the form phi n plus 1 or phi n minus 1. Another interesting problem that arises from this phi n function is this. The set of primes p for which p minus 2 divides 2p minus 3 is finite. In fact, we have verified by programming that up to 10 raised to power 10, we only find 3 primes, 3, 7, and 4, 3, 2, 7. 4, 3, 2, 7 is also prime. And this actually this problem comes from Samuel torsion function, for which de Cornish conjecture is there, that S2p divides phi n minus 1 or not. Next, we have the density. So naturally, we can ask the density of the sequence phi 1, phi 2, phi n. So the density is clearly 0. So the natural question arises from here is the motivation behind this question is the Green's-Tau theorem. Because the density of prime is 0, so that we ask whether the primes contain long arithmetic progression or not. So the same question we ask for, does this set contains long arithmetic progression or not? By programming, we have checked that there are like up to some large number, there contains many 3-term arithmetic progression in this set, but there is no evidence of 4-term or 4 or more than 4-term arithmetic progression. So yeah, but surprisingly, if p and 2p minus 1 is prime, then these three phi p, phi 2p minus 1, phi 2p is always a 3-term arithmetic progression. But we really don't know whether there are infinitely many primes of this type or not, like p and 2p minus 1 are prime or not. So this is again an open problem. Another interesting fact about this function is phi n is not an even perfect number except 6. The sequence is like a kind of lonely sequence. Earlier we have observed that phi n is not a perfect square, and in this case we have observed that phi n is not a perfect number except 6. And later, we raised this problem in our recent article, but Sagar already solved this problem that phi n is equal to Fibonacci number or not. So except 1 and 2, like Fn, phi 1 and phi 2 are Fibonacci numbers. Other than that, there is no Fibonacci number such that phi n is equals to Fibonacci number. But we really don't know whether there are infinitely many factorials of the form phi n or not. Up to 10 raised to power 5, we have already checked. There are only 3 such n exists, such as n equal to 1, 2, 3, such that phi n is factorial. So that's why we said that this sequence phi 1, phi 2, phi n is a kind of lonely sequence, because this does not contain squares, this does not contain even perfect number, this does not contain Fibonacci numbers, or maybe we are according to this 10 raised to power 5, or by programming we have checked this may not contain factorials also. So this also raises like we can also ask several other properties of this function, like whether this contains some other sequence or not. Another interesting function that arises or connected with this phi n function is the number of monic irreducible polynomial. We can calculate this through this formula. And if we substitute q is equals to 2, then this is nothing but phi n over n. Because this q equals to 2 gives you the Nathanson torsion function, the formula which was given by Nathanson. So from here also we can see n always divide phi n, which we have already proved. So it is also interesting to study all the results that we have proved or open problems that we have mentioned for this particular function. So these are references which I have used. Thank you.
Thank you, Mohan. Are there
you.
questions? Oh,
No. Very nice results, I think.
Yeah, thank you.